Welcome back to part 5. I think we're up to part 5, example 3. Okay, here we have a 4.5 meter long floor beam, B1, which supports floor dead and live loads, as well as the non-load bearing walls above. The load here is considered to be partially uniform distributed loads. The floor joist's height is 300 millimeters, and there's also a bulkhead which allows the beam B1 to sit underneath the flooring. Now, for the sake of this example, hypothetically, let's say B1 was initially supposed to be a 2 by 290 by 45 F17 KD hardwood, which gives a long-term deflection of about 12.75 millimeters, and and on site it looks like this. The combined built-up members were made up of 3 elements, and we have this type of shape here. It's like a T-beam, a 290 by 45 F17 KD hardwood, and on either side there is a 240 by 45 F17. And the members are fixed together with M10 bolts at 450 millimeter centers. The combined members passed in serviceability and strength. Okay, so we looked at that. The aim, of course, is to check the connection and the fixings. Okay, here we come down to the beam model. We have W1 star, which is the loading on the left side is 5 kilonewton per meter, and this is factored loads, and W2 star is 8 kilonewton per meter. The reactions FYA is 11.76 kilonewton, and FYB is 14.37 kilonewton. So here we have the shear force diagram, and I've worked out also the averages. So the average shear force for this left span is 5.87 kilonewton, and the average for the right side is 7.18 kilonewton. The shear force at the change of loading between 5 and 8, 5 kilonewton and 8 kilonewton, is 4.77 kilonewton. Now, coming down to the design fixing information, we are given M10 bolts, and the shank diameter is 10 millimeters. This is what's been used out on site. The shear capacity per M10 fixings in the timber is given to us as 1.85 kilonewton per bolt. So this is not the capacity of the actual bolt. This is the capacity of one fixings, okay? And also, this is the capacity for single shear, if the bolt were to shear in a single location. For bolts in double shear, the capacity will be double, which is 3.7 kilonewton per bolt. Now, this also accounts, the capacity of this fixing accounts for the joint group JD3, and it is seasoned, and the timber load is also perpendicular to the grain, and the K1 duration load factor is 0.57 for the worst case loading combination of 1.2 G plus the long-term factor times the live load. Just to recap what single shear and double shear, if you have a look here on our right, a single shear is basically if the bolts shear in one location only. So if we take this hatched part away from the rest of the section, then the bolt capacity we take in this case would be 1.85 kilonewton. It will be a single shear capacity. If we decide to take the middle part alone, then we separate both members away from the middle part, and in this case it will be double shear. Okay, so the bolt will shear into 2 locations. and the capacity of that fixing will be double. And of course, in the last detail is very similar to the first one. We have a single shear through the bolt. And this is very important to note because we will need to use this as part of our example. We will speak a little bit about it as we go through the example. Okay, what else do we have? We have the elevation of the beam, where the bolt end distance is 10d, which seems okay. So 10 multiplied by the shank diameter, and that's 100 millimeters. And the edge distance from the top is 5d, that's 5 times 10, 50 millimeters. And from the bottom, it's generally the minimum is 4d, but in this case we have 50 millimeters. So 4d is 40 millimeters, but we have 50 in this case, which is satisfactory. And it is spaced at, of course, 450 millimeters. I think the maximum spacings, according to AS 1684.2, should not be greater than 2 times the beam depth, where, if the beam depth here is 240, so the maximum spacings cannot exceed 480 millimeters. But this is just a guide that the code has given. Okay, now, so we're all good when it comes to that sense. And of course, the question for this presentation is check if 2M10 bolts at 450 cents is satisfactory. All right, now we need to work out the shear stress and the shear flow. Step 1, select the design shear force that you will be using. Now I have adopted here a conservative shear force value of 14.37 kilonewton. Obviously, because of UDL loads, we could have used the average value, which is half that maximum shear force, which works out to be about 7.18 kilonewton. However, for the sake of this example, I thought to stick with the maximum value right through to be conservative. So it's like having a beam with a point load, and you have a continuous shear force of 14.37 kilonewton. Okay, so far so good. Now let's go to the shear stress and shear flow equation. Going down. Now, the second step is to determine the moment of area Q. And this is the tricky part in this kind of situation. Where do we take, which member do we consider to calculate Q about? Remember, I've named it. I've noted it as AA, BB, and CC. So which member would you take Q about? Have a think about it. Well, to be honest, you can take it around any member, and we will display here how it works. I'll try to explain it as simple as I can. Okay, the first step is to determine the centroid YC of the whole section. And then the second step is to determine Y bar, okay, of the section that we select to calculate Q about. Now Q is dependent on, of course, the direction of the bending, whether it's bending about the major or minor axis. And if it's bending about the major axis, then Y bar will be vertical. The distance between the geometrical centroid of the whole section and the centroid of the element that you choose will be vertically. If it's around the minor axis, then Y bar will need to be horizontally. Okay, so that's the first thing that we need to look at. Then what we need to do, let's say we want to start with element AA. Okay, let's say we take AA. What we need to do is separate the member AA from the rest of the section and then work out the shear flow Q between the planes that you selected. Okay, so to take AA, we take it apart, leave BB and CC together, and then work out the shear flow that is happening in between the fixings. Okay, We might do it step by step so that we do not get confused. Let's work out Q, which is A bar multiplied by the sum of A bar multiplied by Y bar. In this case, if we take this element AA out, we have 240 multiplied by 45, and that will give us an area of 10,800 millimeters squared. Y bar is simply 129.42 minus 120, and of course 120 is the centroid of that element here that we are working with, and that will be 9.42 millimeters. So Q, if we multiply both together, we will get 101,736 millimeter cube. The third step is determine the second moment of area of the whole section of the three elements together, and that will be 2 times 10 to the power 8 millimeters to the power 4. And then the fourth step is determine the width T of the section where shear stress is considered, and again the width is perpendicular to the direction of the shear flow. So in this case the width is 240 millimeters. Now the fifth step, determine the shear stress and shear flow. Okay, shear stress, if we remember, VQ over IT, and then we have 14.37, which is the shear force that I am working with, the most conservative shear force, multiplied by 1,000 to convert everything into Newton, times the first moment of area, divided by 2 times 10 to the power 8, which is the second moment of area, times the width, which is 240, and that will give us 0.03 MPa, Newton divided by millimeter squares. The shear flow, we are multiplying the shear stress by the width, and that will be 7.31 Newton divided by millimeters. So Newton millimeters, okay? It's not divided, it's more 7.31 Newton millimeter one of the length of the beam at that shear plane, at the shear plane that we have considered. So then the total horizontal shear force in the entire plane, in that single plane, is 7.31 multiplied by the length of the beam, and that will give us 32895, which is 32.9 kilonewton. Going through that plane here between AA and BB. So the total shear force just means that we have half the beam, through shear force. When you consider shear force, it's like taking scissors and you're cutting through a paper. So the shear force slides over each other. So that means half of it will take 16.45 kilonewton and the other half will take 16.45 kilonewton. Now a shear force is a little bit different than two forces equal and opposite forces. Shear usually slides over each other. Alright, now so here we have two M10 bolts passing through the plane that we are studying. Therefore, each row, because we have 2 rows of bolts, therefore each row would have to resist 32.9, divide that by 2, would have to resist 16.45 kilonewton. Now we have bolts in single shear. In this plane here, now the shear flow is into the page. Okay, so it's going to, the bolts will only shear at one location. So we have bolts in single shear, and the capacity of each bolt of the fixings is 1.85 kilonewton. Therefore 16.45 divided by 1.85 will give us about 8.89. So that means we need about 9 bolts in each row. For a beam length of 4,500, then we can space out the bolts at 500 centers. So 4,500 divided by 9 is 500 centers. Now remember, this is a spacing, again, it's conservative, because we've taken the most conservative design shear force of 14.37. If we had used the average value, we could actually space the bolts almost at a meter. Okay. However, we will stick to the maximum internal spacing that is given to us in the code, which is 2 times the beam depth. If we're using 240, so it will be 2 times 240, and that will be 480. So therefore, 450 centers is satisfactory. Okay, now, what if we want to take Q for around members CC? So someone might say, okay, what if I do it around CC instead of AA? Same sort of idea. It's the same as before. So we separate member CC away from the rest of the section. So AA and BB are together. We take CC apart, and everything will be exactly, if we work out Q and A and Y bar and all of that, everything will be exactly the same as previously as we did for element AA. So that will give us exactly the same results. And remember, it's symmetrical. So the centroid will be exactly the same, and even the relevant Y bar, so the distance between the centroid of the hatch area and the entire area is exactly the same. So, and even also, and the width 240 is exactly the same. If we had another member with a deeper width, then it might be a little bit more different because the width will change. But in this case, 240 is symmetrical on either side, so we can leave it as it is. Now, what if we want to take Q around member BB? Now this might be a little bit different. However, would that give us the same results? Have a think about that one. And I think the concept is the same for every problem. The first step is work out the centroid of the whole section. And then the second step is take the member that you're interested in, take it separately from the rest of the members. So we can do it the same with element BB. So if we take BB and separate the rest of the elements from it, then we will look at it and say, okay, how many shear planes do we have now running through the fixings? In this case, we have 2 shear planes, not 1. So the bolts will shear at 2 locations, and we will have shear flow on either side of element BB. Previously, we only had 1 shear plane. Okay, see the difference? Let's see what we can do to work this one out. We work out the centroid of the whole section, which is exactly the same, 160.58 millimeters. And Y bar this time will be different. Okay, Y bar in this case now will be 15.58. Again, Y bar is the distance between the area that we are interested in, that hatched area here, and the centroid, the geometrical centroid of the entire section. In this case, it's 15.58 millimeters. So what is the first moment of area? We have the sum of A bar multiplied by Y bar. So A bar in this case is 290 by 45. That's 13,050 millimeters squared. Y bar is 15.58. Q will give us, if we multiply them together, will be 20,3319 millimeter cube. The second moment of area is exactly the same. It hasn't changed. So that's 2 times 10 to the power 8. Okay, now to the shear flow. Now, the shear flow, VQ over I, we now have multiplied this base here by 2. Why do you think we've done that? Because we have 2 shear planes now. So we're basically distributing the shear flow onto 2 shear planes. So Q in this case will be 14.37 multiplied by 1000 multiplied by Q, and this is the shear flow multiplied, so the shear force multiplied by 1,000 to convert it into Newton, multiplied by the first moment of area, divided by 2, which is 2 shear planes, times I, which is 2 times 10 to the power 8. And that will give us 7.31 Newton millimeters. Exactly the same as the previous results, but in this case, we will have a shear flow on either sides of the element B of 7.31, of element BB of 7.31 Newton per millimeters. The total horizontal shear force in each plane is 7.31 times the length, 4.5, and that will be 32.9 kilonewton. Same as the previous answer, but in this case, it's per plane. And remember, in this case, the bolts now will shear into 2 locations, so we will have double shear. So the capacity of the fixings in this case will be double, which is 1.85 times 2, and that will be 3.7 kilonewton. Okay, so if we were only to look at one side of element BB, assuming that the bolts will only shear in one plane, for argument's sake, then what would we have? We'll have 32.9 divided by 2 rows of bolts, and a 16.45 per row, and the number of bolts required will be 16.45 divided by 1 multiplied by 1.85. Why do we put 1 there? Well, because it's one shear plane, because it's going to shear only in one location, and that would be 9 bolts. So that's equivalent to having 2 M10 bolts at 500 centers. And if we have 2 shear planes like what we have here, exactly that same scenario we have here when we pulled out the element BB away from the rest of the section, we have then 65.8 divided by 2, which is 32.9 per row, 32.9 kilonewton per row. Therefore, the number of bolts required will be 32.9 divided by 2 multiplied by 1.85. And we put 2 here because there will be double shear. For each bolt, we'll experience double shear, okay? And guess what? It gave us the same answer of 9 bolts. Therefore, it's equivalent to 2 M10 bolts at 500 centers. So, to summarize, in this situation, it's probably a lot easier to maybe take element AA away from the rest of the section, or element CC away from the rest of the section. It's a lot easier to work out this way. Okay, someone may ask, well, what if I wanted to take Q about elements BB and CC together? Can I group these 2 elements together and separate them from the rest of the section, like this hatched area here? Have a think about it. And if you were to do it this way, then what centroid would you use to calculate the first moment of area? And can I consider these 2 areas here? Can I add them together and consider it as A bar? What do you think? The simple answer to this question is no, because elements BB and CC are individual elements, and the fixings are passing through these individual elements. Okay, so the only way to consider Q around this hatched area is if they are fully bonded or originally in one piece. And if that's the case, then the bolts are only passing through 2 elements, and there is only a single shear. And because it's one piece, then we can calculate the centroid of this hatched area, Y1, as we have here, as well as A bar of that full area. Okay. YC, the geometrical centroid of the entire three elements, will stay the same. And of course, Y bar is the distance between the two centroids together. Okay, let's quickly check if this theory actually works. So if we separate element AA from the rest of the section, like we did previously, and do the shear stress calculation, we will get a shear stress value of 0.03 MPa, which of course we have shown earlier in the presentation. If we are to separate this bonded area now away from the rest of the elements, which is AA, and determine the centroid of that hatched area, we worked it out to be Y1, we worked it out to be 156.32 millimeters, where YC, again, it's still the same as 160.58 millimeters. A bar then becomes 290, this whole area, 290 multiplied by 90, minus that little bit there, which is 50 multiplied by 45. Okay, that will give us 23850 millimeters squares. And Y bar is simply 160.58 minus 156.32, and that will be 4.26 millimeters. The first moment of area Q then simply is the product of A bar and Y bar, which will give us 101,601 millimeter cubed. The second moment of area, I, of the three elements unified together is still the same as 2 times 10 to the power 8 millimeters to the power 4. And remember, T in this case, the width, which is perpendicular to the shear flow, and the shear flow is into the page, it's not 290, okay? Try not to fall into this trap. It's still 240, okay? There's no shear stress in this little section here. The shear stress acts where the elements are in contact by the fixings, which are the bolts in this case, okay? And this, be careful here because we do a lot of mistakes in that sense. Okay, now what do we do? So we work everything out. Tau shear stress is equal to VQ over IT, and we get exactly the same results of 0.03 MPa. Wow, I just hope you are as happy as I am now, because I'm glad this this theory works. Yeah, and I think I think this is the end of my story. I hope this sort of made sense. It is a little bit tricky when we're working out the first moment of area around these complicated sections. So in the next video, hopefully in the next video, this will be our last video with this presentation of the shear stress. We will look at a symmetrical boxed up beam, a timber boxed up beam. Sometimes in residential buildings, we need to create these boxed up beams, boxed up members, either to form part of a roof structure or a wall facade system, or sometimes we position it under a bulkhead to support a particular feature. In this example, we have a 3 meter long boxed up timber beam with a permanent dead load, point load, that acts as a point load. Now, I want to pick your brains here for a second. Which built up member would you choose for the best fixings, if you like? Best case for stability and strength and fixings condition. Which one would you choose, A, B, or C? And we will be using screws in this case. Now you can see that A has vertical screws, combining the top part to the top horizontal part to the vertical parts. In the second one, we have a combination of vertical and horizontal screws. And in the third section, number C, we have horizontal screws only. So yeah, so I want you to probably think about it until next time. Please stay tuned. In the meantime, if you have enjoyed this video and found it useful, please share and subscribe so that others may also learn. Until next time, we hope you have a great afternoon.